Electron configurations tell us where electrons can be found around the nucleus in an atom. Electron configurations are based on the quantum mechanical model, which is based on calculus that we're not going to worry about in this class, but it predicts the most likely place to find an electron in an atom. Electrons jump around specific energy levels of an atom. We call these jumps quantum leaps. When an electron jumps from a lower energy level to a higher energy level, it is moving to an excited state, a state that has more energy. In this case, the electron gains energy. The electron might gain energy from heat or a more powerful light, electricity, something like that. When an electron falls from a higher energy level to a lower energy level, the electron loses energy. We see this loss of energy in the form of light. The lower energy level is called the ground state, or the lowest level is called the ground state. So the color of light depends on how much energy an electron gives off when it falls. If it's red light, it's not very much energy. If it's something like violet light, it's a lot more energy. And other parts of the electromagnetic spectrum fall into that category as well. We can determine how many orbitals there are for a particular atom by looking at its total number of electrons and number of valence electrons. Remember, the group number dictates how many valence electrons there are. And I'm going to show you another way of figuring that out as well. So we talked about a wave in class, and s orbitals are kind of like if you took a wave and spun it around super, super fast. So for example, the first kind of orbital is like half a wavelength spinning around the x-axis. So if we could get this shape to spin around at the speed of light, we would get an s orbital. An s orbital is just a sphere with some shading in it. So it needs to look three-dimensional. In real life, it doesn't have shading. It's just to help remind you it's supposed to be a three-dimensional shape. So we say S stands for sphere. A p orbital, that's a full wavelength. That's not a great example, but it's like if you took a full wave and you spun it around in 3 dimensions. It looks very much like an infinity symbol. You can kind of shade that in as well and make it look a little bit three-dimensional. It's hard to do it on the computer. So we say the p orbital kind of looks like a peanut. A d orbital is an even more energetic wave. So it kind of looks like this. But this time it's spinning in 2 different dimensions. So one of the waves is straight up and down, and the other wave is going across this way. Again, not my best drawings. You can do a better job probably on pencil and paper than I can on here. So the d orbital's nickname is the daisy. Here are examples of all the types of orbitals: s, p, d, and f. We didn't even try to draw an f orbital because it's really, really complicated. I want you to draw an arrow going down the page, and that arrow represents an increase in energy. So s orbitals have the least amount of energy, and you can kind of tell by looking at it because they have really uncomplicated wave. Each orbital can hold 2 electrons. So that one s orbital can hold 2. Each of these p orbitals can hold 2 electrons. And so forth as you move down the page. Each d orbital can hold 2 electrons. So even though their shapes are very, very different from each other, they can all hold 2 electrons. Even these very complicated shapes in the f orbitals. You don't even have to draw these 2 electrons in if you don't want to. I'm just doing it for emphasis to show you. So you can see on this periodic table that there are 4 different sections: an S block, a P block, a D block, and an F block. And the number in front of them represents their energy level. So if we look at the first row of the periodic table, or the first energy level, we can see there are only S-type orbitals in that row. And each box represents 1 electron. So the first row has 1, 2 electrons. And you may remember from middle school or maybe even elementary school, your teacher telling you that in an atom the first ring has 2 electrons. Well, this is where that came from. The second energy level has both S and P sublevels or orbitals. And if you count up all of those boxes, there's 2 in the S, there's 1, 2, 3, 4, 5, 6 in the P. That adds up to 8 electrons. In the third energy level, something very strange happens. We have s orbitals, we have p orbitals, but we also have d orbitals. And they're in a little bit of a different spot, but all of those still belong in the third energy level. So we have s, p, and d. If you add up all the boxes in the s level, the p level, and the d level, they will add up to 18 electrons. The fourth energy level has 4s, 4p, 4d, and 4f. And on your long form periodic table, you can see that this F block is really wedged in right in here. So there's S, P, D, and F. And if you were to count all those boxes up, it adds up to 32 electrons. The fifth energy level is the same way. S, P, D, and F, and is also 32 electrons. The sixth has S, D, and P, but no F, at least not yet. They may make some elements that have electrons in the 6F energy level, but it hasn't happened yet. So it's S, I'm just going to write it over here, S, P, and D, which adds up to 18 electrons, and that was supposed to be 32. And energy level 7 has S, and it's not on this version of the periodic table, but it actually also has p orbitals. This just might be an older version of the periodic table, and that has 8 electrons. If you turn to the next page in your notes, you'll see a diagram that looks like this, and a silly title called the Aufbau Hotel. And in German, Aufbau means building up. So if this diagram of a hotel looks somewhat like the periodic table to you, there's a reason for that. It's to represent the different parts of the periodic table. So in this hotel, there's some rules about how the rooms can fill up. First of all, the real life name of this is Hund's rule, or we call it the roommate rule. So electrons do not like to share orbitals if they don't have to. And that's much like you probably don't want a roommate unless you absolutely have to have a roommate. Okay, the maximum occupancy for every room or orbital is 2 electrons, and we already talked about this. One of the electrons is going to be represented by an up arrow, and one of the electrons is going to be represented by a down arrow. So in this hotel, the rooms are added from the bottom floor, the hydrogen room, which is right here, up to the top, and they must fill from left to right. So much like on your periodic table you have that I gave you the long form of the periodic table, this is 1s right here. So we're just going to make a silly analogy and say that the S rooms will be the super rooms. They're only $1 sign, not very expensive. The p orbitals will be the, I don't know, pretty good rooms, which doesn't sound as good as super, but that's okay. They'll say they're $2 signs. D will be deluxe, and they're $3 signs. So we have to fill up this whole bottom part of the periodic table before we can get to the d orbitals. So in the first box, this room right here is actually connected, even though they're on two sides of the hotel. So this is where the analogy gets a little bit weird, but just stay with me. So in this first room, there are two beds. One person is going to have a day schedule, which is represented by an up arrow. The other person is going to have a night schedule, which will represent by a down arrow. So even though these electrons have to be in the same room, they want to be on different schedules because they don't want to be in the room at the same time as each other. Okay, the next room to fill will be 2s. So this will be this room right here. So we'll have an up arrow and a down arrow. Then you're going to go all the way across the periodic table to here. This is 2p. Now, 2p has three different orbitals, or three different rooms. So here's one, and here's another one. So we're going to fill these rooms individually first, because we said electrons or people don't like to share rooms or orbitals if they don't have to. So all of these rooms right here are equally valuable. So the first room is going to have an up arrow. Sorry, I don't know why that thing keeps popping up on here. The next one's going to have an up arrow and an up arrow. So each of these individual rooms are now full of one electron. But another electron is going to come in each of these rooms and be on a different schedule or go in a different direction. And this is how the whole entire periodic table fills up. Now it's a little bit hard to understand sometimes from this analogy, and so what we'll do is a lot more practice problems with this so you can understand what's going on here. So the different schedules rule is called the Pauli exclusion principle in real life. It just means that electrons have opposite spins. And in real life, there really are two electrons, and the two parts of the wave, or two electrons in there, are spinning in different directions. We can show the configuration or arrangement of electrons, or these orbitals in atoms, through models and through a written shorthand. It's kind of like a barcode for chemistry. So the first thing you're going to do is write down the energy levels. So let's say we're talking about helium. Okay, helium lives in the first energy level, or the first row of the periodic table. Then you're going to include the orbital type. So helium is in energy level 1, and he's in an orbital s. Then a superscript showing the amount of electrons in that orbital. So helium's in energy level 1, orbital type s, and he has 2 electrons. Or he's in box 2 on the periodic table right there. So for example, oxygen has 8 total electrons. Now you're going to start at the very, very beginning of the periodic table and walk your way through the whole table. So let me show you what this looks like on the back page of your notes. So here's oxygen right here. So your configuration for oxygen would be 1s2. There's a box there and a box there. Then we go to the next row. 2s2. There's 2 boxes here. Then we follow this all the way across. We run into 2p. And oxygen's in the fourth box over. So we just count over 1, 2, 3, 4. And it's 2p4. Okay, so let's put that back on your notes page. So it's 1s2, 2s2, 2p4. Okay, to figure out how many valence electrons this particular atom has, find the two, well, it's not always two, but just find the higher energy level numbers. So in this case, we have 2's, and then add their superscripts together. So 2 plus 4, oxygen has 6 valence electrons. Okay, let's look at aluminum. Aluminum is number 13. So you can follow along on your periodic table. I'm not going to refer back to that right now. I'll just walk through it with you. So aluminum's 1s2, 2s2, 2p6, 3s2, 3p1. If you look on your periodic table, in row 3p, aluminum should be in the first box. So, for the valence electrons, again, we look at the two highest energy levels. In this case, there's 2 of them. There's 2, 3 energy levels. You add these two numbers together and you get 3 electrons. Okay, we'll have to look back at the periodic table to find calcium. Calcium should be right in here somewhere. I have to pull up my real periodic table so I can find out. So calcium's atomic number is 20. So again, we always start at the beginning. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So if you add all these numbers together at the top, they should add up to 20. So 2 plus 2 plus 6 is 10, 12, 18, 20. To figure out how many valence electrons it has, all you need to do is look at the highest energy level. In this case, it's just 4. He has 2 electrons, so he's got 2 valence electrons. Now there's an easier way to do this, and chemists are pretty lazy, so we like to take the easy way out if we can. So if you turn the page in your notes, I'll show you how to do this much more quickly. The easiest way to learn how to write electron configuration is to practice it. The shorter hand version of doing this is called the noble gas configuration. So if you look back at your periodic table, remember the noble gases are helium, neon, argon, krypton, xenon, and radon. So the thing you're going to do this time is you'll find the last noble gas in atomic number before the element you are describing, and that noble gas will represent the whole electron configuration up to that point. So find the orbitals following the noble gas, and we're going to show them. So if you look at aluminum, aluminum is number 13 on the periodic table. If you go backwards from aluminum, the first noble gas you're going to run into is neon, who's number 10. So you're going to put neon in brackets, and that is to represent 1s2, 2s2, and 2p6 for neon. Then all you have to do after that is fill in the remaining parts of the configuration to get to aluminum. So that would be 3s2 and 3p1. And this makes it super easy to figure out how many valence electrons you have because they're just right here. Okay, I don't know why I picked this one because it's really easy. It's right next to aluminum, but phosphorus is 15. So you're going to go back to the same noble gas, which is neon. And phosphorus will be 3s2, 3p3. And from this you can tell he has 5 valence electrons. Okay, pause the video right here. I want you to try and do bromine on your own. Okay, so bromine has 35 electrons. Now, you may be thinking, oh, I'll just use krypton and subtract. But you can't do that. You have to go back to the next noble gas, or you have to go backwards. So the noble gas before bromine is argon. And after argon, you should have 4s2. Then it goes to 3d10. And bromine is in 4p5. Now this is a funky anomaly on the periodic table that it goes from energy level to 4 to energy level 3 and then back to 4, but that's what happens. So now you can look at these two orbitals. If you add together their exponents, you'll end up with 7 valence electrons.
Okay. All right, so let's talk about the exceptions you're going to face when you're dealing with electron configurations. There's going to be a few of them, but we're going to talk about the main ones you're probably going to see in class. All right, so let's talk about chromium. Chromium is a transition metal. It has 24 electrons, and here's the orbital diagram. If we were to make this shorthand and make the electron configuration for this, we would make this 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Okay. From now on, every time you see 3d4, you're going to change it. We do not like 3d4. The D sublevel is most stable when it's either half full, all the electrons are, all the orbitals are filled with at least one electron, or completely filled. Right now, we're 1 electron short of it being halfway filled. So what we're going to do is that should be a 2 there, sorry. We're going to take one of the electrons in the 4s orbital and move it over to the 3d orbital. So instead, we're going to write, actually, we're going to make this argon, as we noted before in the noble gas configuration. And we're going to make this 4s1 3d5. This is halfway filled, which is pretty stable, and this is much more stable being halfway filled rather than being the d4. You might see, this is the diagram that you're going to, or the electron configuration that you're going to see, and this is actually higher in energy than this. So this is talking about sequential, or not sequential, but like the order of energy. You might see it also looking like this. This is just doing it in order of numbers. 3 comes before 4, but they're exactly the same thing. They're depicting the exact same thing. Nothing's different between them. So you might see either one, but they're the same. Down here, the other exception you're going to see is copper, or anything along copper, which we'll talk about. Okay, so let's make the electron configuration for that. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. From here on out, anytime you see d9, we're going to change it. Okay, so anytime that it ends in d9, we're going to fix it up a little bit. Same exact way. We're going to take an electron from the 4s and we're going to move it over to the 3d. That way, this d orbital or d sublevel will be completely filled, which is very stable, and the s orbital will be halfway filled. So again, I'm going to make this argon just to make it easy for myself. 4s1 3d10. And again, you might see it as argon 3d10 4s1. Same exact thing. So those are the exceptions, the main exceptions that you'll see when dealing with electron configuration.
You can also have electron configurations for ions, and this is extremely helpful in trying to figure out down the road how things are going to bond. So for example, sodium normally has 11 electrons, but if it's an ion and has a positive charge, it means it's lost one of those electrons, so now it only has 10. So I'm going to show you how to fill out this chart with those electrons. We're going to do the first box first. 1 up arrow, 1 down arrow for those 2 electrons that live in the 1s orbital. So it's totally done, so we're going to move over here to 2s. These should be lined up a little better, but they aren't. He gets 1 up arrow, 1 down arrow. Okay? Then all of these p orbitals are all together. So if we're following the rules, each one of these p orbitals gets an arrow in it first. So they all get their own room first, and then they have to start pairing up. So let's go back and count and make sure we haven't overdone it already. So there's 2, 4, 5, 6, 7. We need a total of 10, 8, 9, 10. So if you actually look at the configuration for this, its configuration is really the same as neon, which is a noble gas. Okay, fluorine has 9 electrons, but it's got a negative charge, so that means it also is going to have 10 electrons. So remember back from a few weeks ago when we talked about the goal of every atom is to get a full outer shell or a full octet. So this one, since he has 10 electrons, is going to look exactly like what we just did. One up, one down, one up, one down, up, 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 down, down, down. And again, it's going to look just like neon. Oxygen has 8 electrons, but if he's an ion with a -2 charge, guess what? 8 plus 2 is again 10. So many ion electron configurations all look the same. Up, 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 down, down, down.